Hey everybody. So we are going to continue the parade of identities, these nice little equivalences with the trigonometric functions. So we're looking at what are called the sum and difference identities. And so what I'm going to do is I'm going to use some geometry to derive one of them, and then the rest we will take on faith. They're similar ideas. There's lots of different ways to come at these. This gives us a little bit of an intuition around it, maybe. You don't need to be able to compute it or discover it this way. What's most important is being able to use these identities, which we will get to at the end and in following videos. So I've started with a drawing here. I've just got the top half of the unit circle. Maybe I'll label a point to make that clear. This is the point 1, 0. And I want to label some angles here. So I'm going to call this angle beta to that first red line. And then the angle here will be alpha. And notice that that makes this angle here alpha minus beta, right? It's as big as alpha, except taking off that part that is beta, okay? So now with those three angles there, I want to label a couple of points. So from our trig definitions, we know where this first ray intersects the unit circle. Its x coordinate will be cosine of beta, and its y coordinate will be sine of beta. This one will be similar, cosine alpha, sine alpha. And then I'm going to draw a line across connecting these 2 points. Whoops, let me do that again. Okay. So there we see I've made a little triangle. Now notice that this triangle has the vertex of this triangle that's at the origin is that angle alpha minus beta. Okay, so we're going to use that idea in a moment. I also want to give a name to the length of this. So let's say maybe yeah, I'll just call this length, the one across from alpha minus beta, I'm just going to call it L1, okay? Now, here's where we have to imagine a little bit. Why don't we take this angle? What I want to do is rotate this triangle, excuse me. So I'm going to keep that vertex at the origin there. And I want to rotate the triangle so that it's this edge that is making angle beta now rests on the y-axis. So we'll have a side here. Actually, sorry, let me make that a little thicker. So that ray that used to be pointing out in the direction of angle beta, I've turned it this way, right? I've rotated it clockwise. So imagine what that will do to this ray over here is going to rotate it somewhere over there. So I'm trying to just approximate, make it the same amount of rotation that we have of this one. So that ray might go somewhere about like this, okay? And I want to consider, right? So again, this blue triangle is supposed to be imagining rotating this red triangle by an angle of alpha minus beta, okay? All right, let me zoom in and erase a couple of things to make this easier to look at for a second, because I want to add some more. Oh, I guess it doesn't let me go over there. Well, let's see what I can do. So I'll keep alpha minus beta there. I want to get rid of this one as much as I can, and this one as well. We'll have to deal with a little mess until I learn how to use this better. Okay, So let's now look at this blue triangle. Because we've rotated the whole triangle, this angle here should still be the angle alpha minus beta, right? That triangle, I'm imagining it staying rigid. So that angle is alpha minus beta. Let's put in coordinate points. We already know that we rotated this ray down to the point 1, 0. This right here now will be cosine alpha minus beta sine alpha minus beta, right? Just from our definition of the trig functions. And I'll call this blue line connecting these vertices that are on the unit circle L2, okay? All right, so now we're gonna do a little bit of algebra, okay? The big idea is let's look at L1 and L2, okay? Those two lengths, that's the same triangle rotated. It has to be the case that L1 is equal to L2, okay? So let's look at each of those lengths. And what we're going to use is the distance formula, right? So if you remember the distance formula between 2 points, maybe I'll write it up here. Our distance formula between the points x1, y1, and x2, y2 is given by, we take the difference in the x coordinates, square it, take the difference in the y coordinates, square it, and we take the square root of that whole thing. That's our distance formula, right? It's really just comes from the Pythagorean theorem, or you can see it's the same idea. I've mentioned this before. Distance formula, Pythagorean theorem, and the equation of a circle are all getting at the same idea, but I'm just going to take this as a formula for now. So let's look at L1. We've got these 2 points. I'm looking at the red vertices here and here. So if I want the distance between those 2 points, I'm going to take the difference between the x coordinates, square it, take the difference between the y coordinates, sine beta, square it, and take the square root of the whole thing, okay? So let's do a little bit of algebra here. So L1 will become, so if I expand this thing, it's going to be cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. And do the same thing to the y terms, the sine terms. We'll get plus sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. Okay, and now let's do a little simplification here. Let's notice a couple of things. Cosine squared plus sine squared alpha. So we've got the cosine and the sine squared of the same angle. That gives us 1, right? We know the Pythagorean identity, that's equal to 1. We've got another pair like that here. So those 4 terms, each pairing is equal to 1, and we've got 2 of them, so I've got 2. And then I've got these terms, minus 2 cosine alpha cosine beta, minus 2 sine alpha sine beta. I can factor the negative 2 out of them, and I've got minus 2 cosine alpha cosine beta plus sine alpha sine beta. And all of this is still happening inside that square root. Okay, so it simplifies down fairly simply. Okay, all right, now let's leave that alone. We're going to come back to this. Maybe I'll give this a little box for us to just know where we need to come back to. We'll use that later. And let's look at L2. and do the exact same game. So now I'm looking at this vertex and this vertex because they're the same triangle. These lengths are going to be the same. So I want to look at the length of L2. So again, I'll start with the difference in the x coordinates. So the first x coordinate up top there is cosine of alpha minus beta. And the other x coordinate is 1 squared. And then the y coordinate is sine of alpha minus beta. And then we're subtracting 0. The other y coordinate is 0, so I'm just going to leave that off. And we're squaring that, and we've got to the 1/2 power. All right, let's expand this. I'll get cosine squared alpha minus beta minus 2 cosine alpha minus beta plus 1 plus sine squared alpha minus beta to the 1/2. And we're almost there. We're going to play a similar game. Cosine squared alpha minus beta plus sine squared alpha minus beta. So don't worry about how complicated the argument of cosine and sine are, that alpha minus beta. Alpha minus beta is just some angle, and they're the same angle. Whatever alpha minus beta is, it's the same thing. So if you take cosine squared of an angle and sine squared of an angle, you're going to get 1. And we already have another one right here, so we'll get 2. And then I've got this minus 2 cosine alpha minus beta to the 1/2. Okay, so there's a nice compact expression for that other distance. All right, we're almost there. So here is the big, I don't know, the big something. The fact that these two things are equal means, I'm gonna come up here, I can take this, what I have boxed in red, 2 minus 2 cosine alpha cosine beta plus sine alpha sine beta, making sure I have it correct. All of this, I might have, nope, that's the right number of parentheses, is to the 1/2 power. This has to be equal to the other length, which is 2 minus 2 cosine alpha minus beta to the 1/2. All right, now we do some simple algebra. We're going to square both sides. So we get rid of those 1/2 powers. So I've got 2 minus 2 cosine alpha cosine beta plus sine alpha sine beta is equal to 2 minus 2 cosine alpha minus beta. Well, now we have a couple simple things to do. Subtract 2 from each side, so that'll cancel both of these 2's. Divide both sides by -2, which cancels these factors of -2, and we end up with cosine of alpha cosine of beta plus sine alpha sine beta is equal to cosine of alpha minus beta. And this is our first of the sum and difference identities. This is a difference identity for cosine. Okay, so if you have the cosine of the difference of two angles, instead you can do this configuration on the left, or vice versa. If you have some configuration like this, you can change it to the difference of the two angles. Okay, so we'll do some examples. I want to give you the rest of the sum and difference that are discovered in similar ways. Like I said, this is a good exercise in geometry. There's some good algebra in here. We have to use our Pythagorean identity, so they're not invaluable, unvaluable. They're not without value. It's not without value to go through this process. But what's most important right now is that we have this identity and that we understand how to use it, which we'll do some examples in just a moment. So I'm going to give us now a list of 6 identities like this. It's really 3 if we understand how cosine and sine work, and I'll show you that in just a second. So let me list them, and then make a couple comments and do some examples. So start with the one we just did. Cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. If we have cosine of alpha plus beta, that's cosine alpha cosine beta minus sine alpha sine beta. We have two of them for sine of alpha plus beta. Why don't I do it in the same order? So I'll start with the minus. It doesn't really matter, but for consistency. So this is going to be sine alpha cosine beta minus cosine of alpha sine beta, and then sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Okay, and then finally we have not secant, tangent. Tangent of alpha minus beta is going to be tangent of alpha minus tangent of beta divided by 1 plus tangent alpha tangent beta, and tangent of alpha plus beta is going to be tangent of alpha plus tangent of beta, 1 minus tangent of alpha tangent of beta. Okay, so there are our sum and difference identities. Okay, so there's 6 of them here. I do want to point out, let's look at this first set, for instance. We have cosine alpha minus beta is equal to cosine of alpha. Just copying it here. Cosine of alpha cosine of beta plus sine alpha sine beta. What if I replace beta with negative beta, right? There's nothing that says beta is positive or negative in this, right? The geometry, the way I drew it was positive, but it works out regardless. Well, so we could, if this was a negative angle, we should be able to replace it with its opposite, a positive angle, and vice versa. So what would happen? Cosine of alpha, cosine negative beta. I'll put that in a second. Well, look on the left, we have minus minus, that's alpha plus beta. Remember the even and odd function identities. Cosine of negative beta is the same as cosine of beta, but sine of negative beta is negative sine of beta. In other words, that beta can slip out and we pull it to the front to get a minus right there. And there's our addition formula. So really, and the same thing happens with all these other ones. If you know it for one of them, as long as you remember the even and odd ideas around cosine and sine and tangent, you can discover the other ones easily, okay? So there's really only 3 of them, and then the negatives work out the way that they should, and they should. All right, let's do a couple of examples. Let's do a maybe not silly example, but just some things to help confirm that this makes sense. So we'll look at some things we already know to be true. So for instance, let's just test this formula on something we know. I know that cosine of 0 is equal to 1. But suppose I wrote cosine in a funny way. Cosine of pi over 4 minus pi over 4. That's certainly 0, and we can think of it as the difference of these two angles. And I apply my formula. So I'm looking up here, I have cosine of, this is like the alpha, this is like the beta, they're the same in this case. So this is cosine of pi over 4, cosine of pi over 4, plus sine of pi over 4, sine pi over 4. We end up with, so the cosine is root 2 over 2, and there's 2 of them, so it'll be squared. And the same thing for the sine. Well, what happens when you square this? You get 2 over 4, or 1/2, plus 1/2, and the formula works out. So obviously in this case, it's not helpful. It wasn't easier to do it this way, but it's nice to see that it confirms, or it doesn't contradict what we already know to be true. All right, let's do a more interesting example. Let's look at the sine of pi over 12. Okay, so this doesn't look like it's a sum or a difference, but what we might notice if we wanted to compute this is that pi over 12, I can think of pi over 12 as 4 pi over 12 minus 3 pi over 12, right? If you take 4 of something and minus 3 of something, you get 1 of something left. You might rightfully ask yourself, why in the world would I write it this way? Well, if we reduce these fractions, this is pi over 3 minus pi over 4. And those are more familiar angles for us. So there's our sine of pi over 3 minus pi over 4. Now we have a difference. Let's go grab our cosine difference formula. Bring it down here for us. All right. So now this is like my alpha. This is like my beta. I can replace this with the configuration we have over here. So this is going to be sine of pi over 3, cosine of pi over 4, minus cosine of pi over 3, sine of pi over 4. And these are angles we know from the unit circle. Sine of pi over 3, that one is root 3 over 2. Cosine of pi over 4, root 2 over 2. And then cosine of pi over 3 is 1/2. And sine of pi over 4 is root 2 over 2. So we end up with square root of 6 over 4 minus the square root of 2 over 4. If we want, we can put this as a single fraction. Root 6 minus root 2 all over 4. Okay, and that gives us an exact value for sine of pi over 12, which doesn't appear on the unit circle, right? But we have a nice exact number here if that's something we need. Point of order, I don't know if that's the right phrase to use here, but anyways, this is not what we use these for. These are good exercises to practice using them and make sure we understand how to put all the pieces in the right place. Mathematicians and scientists don't spend their time calculating things like, what's the sine of pi over 12, right? If you're building the Large Hadron Collider and you need an angle of something, you would use, we have other ways to compute things. We have sophisticated computer software that can do it for us to an astronomical degree of certainty or precision, and you can use that to measure. But what's really important here is that we're playing with these formulas They are very useful when you're manipulating algebraic expressions, or you'll see when you get to calculus, there are certain operations that you might replace one with the other that makes them much easier to compute. Things called derivatives and integrals. And so these can work out to be nice, just really nice tools that we have to simplify otherwise very complicated ideas or computations. Okay, let's do 2 more examples for this video, and then we'll save the rest for another one. Let's do a similar kind of idea with tangent. So tangent of 5 pi over 12. We can do a very similar thing that we did above and realize that 5/12 pi is the same as pi over 6 plus pi over 4, right? Pi over 6 is 2/12, pi over 4 is 3/12, so together that's 5/12. So let's go grab our tangent formula. We have a sum let's throw that down here. Oh, that's really slanted. So using, we have alpha and beta. So I can just map all of these things to the right place. We get tangent of alpha, so that's tangent of pi over 6 plus tangent of beta, tangent of pi over 4, over 1 minus tangent of alpha, pi over 6, tangent of pi over 4. So tangent of pi over 6, if you look at your unit circle, I'm just going to write it as it's 1 over root 3 or root 3 over 3, 1 over root 3. Tangent of pi over 4 is 1. We get 1 minus 1 over root 3 times 1. This is correct. I don't like how it's written, so I'm going to multiply this whole thing by 1 by multiplying by root 3 over root 3. We distribute that, so this becomes 1 plus root 3 over 1 minus root 3. To my mind, that is a much more pleasing way to write this number. Okay, and that's right, the use of this tangent identity, right? So it's just making sure you identify what's alpha, what's beta, and putting everything in the right place. Very last thing, I promise, let's take a look at something we've seen before. We looked at earlier at some cofunction identities. So for instance, we had sine of pi over 2 minus theta is equal to cosine of theta. Let's use the difference formula to confirm this. So this is my alpha minus beta. We know that sine of pi over 2 minus theta, sine of alpha minus beta, was sine of alpha, this is our difference formula, times cosine of beta, theta is our beta in this case, and then we have minus cosine of alpha, sine of beta. Well, sine of pi over 2 is 1, so this is a 1, and we've got cosine of theta. Cosine of pi over 2 is 0, so that whole term disappears, and there we see our cofunction identity show up using the sum and difference identity. Okay, I will stop there. I'll do at least one more example in another video, a little more involved, but that'll do it for now. Thanks everybody. I will see you next time.